Have you ever sat in a room so quiet that you could hear the blood rushing in your ears? Have you ever wondered if that silence was truly empty, or if it was simply a canvas waiting for a painting that your eyes could not see? We live our lives immersed in a constant ocean of noise, the hum of traffic, the melody of a bird, the gentle rhythm of our own breathing. We perceive these sounds as smooth, continuous waves washing over us like the tide coming in on a beach. To us, sound is a flow. It is liquid. It is an unbroken ribbon of energy that connects the speaker to the listener, a seamless bridge across the air. But what if I told you that this smoothness is an illusion? What if I told you that if you could listen with the ears of a subatomic particle, the symphony of the universe would not sound like a violin sliding gracefully between notes, but rather like a billion tiny hammers striking a billion tiny bells. The moon does not spin in the way we think, and sound does not flow in the way we feel. When we peel back the layers of reality and look at the world through the lens of quantum physics, we discover that the universe is not made of smooth lines. It is made of grains. It is made of packets. Just as a beach looks like a solid yellow ribbon from a plane, but resolves into billions of jagged grains of sand when you kneel upon it, sound itself, that ethereal, invisible ghost that carries our voices, is made of something. It has a body. It has a substance. It is built from tiny, discrete chunks of energy that physicists call phonons. And understanding these ghost particles requires us to embark on a journey that takes us from the comfort of our living rooms down into the shivering, vibrating heart of matter itself, where the very concept of quiet ceases to exist. This is a journey into the granularity of existence. It is a journey into the quantum nature of the whisper. And before we can understand the phonon, we must first understand the silence that it breaks. If you enjoy exploring the strangest and most mind-bending mysteries of our cosmos, please take a moment to subscribe to the channel. I am Walter, the Explorer, and it is my honor to be your guide on this quiet journey through the stars and the subatomic void. Currently, 73% of the curious minds traveling with us have not yet subscribed. It helps us bring more content like this to you, and it lets us know that you want to keep exploring the universe together. Thank you for walking this path with us. Now, let us return to the room. Let us return to the air. To understand the quantum nature of sound, we must first look at how we have understood it for thousands of years. For centuries, humanity looked at sound and saw a wave. The ancient Greek philosopher Aristotle, writing more than 2,000 years ago, intuited that sound was a movement of the air. He imagined the air expanding and compressing, a physical commotion that traveled from a source to an ear. He was right, of course, but his vision was one of fluids and continuity. When Sir Isaac Newton wrote his Principia Mathematica in 1687, he attempted to calculate the speed of sound mathematically for the first time. Newton saw sound as a pulse of pressure moving through an elastic fluid. To him, and to the classical physicists who followed, sound was a mechanical event. It was a wave, identical in nature to the ripples that spread out when you drop a pebble into a still pond. Imagine that pond for a moment. Picture the surface of the water, glassy and still under the moonlight. When the pebble hits, the water does not move from the center to the edge. The energy does. The water molecules merely bob up and down, passing the energy along to their neighbors. This is the classical view of sound. It is a domino effect. One molecule of air hits the next, which hits the next, creating a chain reaction of pressure that eventually drums against your eardrum. In this view, sound is an analog phenomenon. It is smooth. You can have a loud sound or a slightly softer sound or a whisper on a continuous sliding scale. There are no gaps. There are no jumps. It is a perfect, unbroken curve of energy. But classical physics, for all its beauty and utility, is an approximation. It is the view from the airplane. It describes the shape of the beach, but it ignores the sand. When we zoom in past the capabilities of the human ear, past the sensitivity of our finest microphones, and down to the scale of individual atoms, the smoothness of the wave begins to break down. We enter the realm of the discrete. We enter the quantum realm. You see, sound requires a medium. It cannot travel through a true vacuum, which is why space is popularly considered silent. Although, as we will discover in later chapters, that is not entirely true either. But here on Earth, sound travels through matter. It travels through air, through water, through steel. And matter is not continuous. Matter is granular. Matter is made of atoms. And this is where the paradox begins. If sound is a wave traveling through a medium, and the medium itself is made of separate, disconnected particles, then sound itself must be broken up into separate, disconnected events. Imagine a crystal. Picture a diamond, or a grain of salt, or even a piece of metal. Inside that solid object, the atoms are arranged in a perfect, repeating lattice. They are like soldiers standing in a grid, row upon row, column upon column. But these atoms are not frozen in place. They are not statues. They are vibrating. They are shivering with thermal energy, constantly jiggling against their neighbors. You can imagine that between each atom and its neighbor, there is a tiny, invisible spring. These springs represent the electromagnetic forces that hold the solid together. When a sound wave moves through this crystal, it is not a mysterious fluid flowing through the gaps. It is a specific type of vibration passing through those springs. Atom A moves, pushing on the spring, which pushes on atom B, which pushes on atom C. But because this system is happening at the quantum scale, the rules of the game change. In the quantum world, energy is not continuous. You cannot just give an atom any amount of energy. This was the great discovery of Max Planck and Albert Einstein at the dawn of the 20th century. They discovered that light was not just a wave, but was made of packets called photons. You cannot have half a photon. You can have one, or two, or a trillion. Light is grainy. It is quantized. And here is the beautiful, symmetrical revelation. Sound behaves the same way. The vibrational energy in that crystal cannot be just any amount. It has to come in specific, discrete packets. The atoms can vibrate at energy level 1 or energy level 2, but they cannot vibrate at energy level 1.5. The universe forbids it. These discrete packets of vibrational energy are what physicists call phonons. The word phonon comes from the Greek word phone, which means sound or voice. It is a beautiful word for a ghostly concept. A phonon is not a particle of matter like an electron or a proton. You cannot put a phonon in a jar and keep it there. If you stop the vibration, the phonon disappears. It is what physicists call a quasi-particle. It behaves like a particle. It has momentum. It has energy. It can collide with other things. But it is actually a collective motion of billions of atoms acting in unison. Think of the wave performed by fans in a stadium. You see a shape moving across the crowd. That shape has speed. It has a direction. You could even say it has a size. But the wave is not a physical object. No single person is the wave. The wave is a pattern of motion emerging from the collective action of thousands of individual people. A phonon is like that stadium wave. but quantized. It is the smallest possible unit of that wave. It is a single quantum of sound. This means that sound is not a smooth slide. It is a staircase. When you turn up the volume on your radio, you are not smoothly increasing the pressure of the air. You're adding phonons to the system, one by one. Of course, at the scale of human hearing, the number of phonons is so astronomically high, trillions upon trillions of them, that the staircase looks like a smooth ramp. We cannot perceive the individual steps. The graininess of sound is hidden from us by the sheer scale of the numbers, but the steps are there, and this has profound implications for how we understand the universe. It means that there is a limit to how quiet a sound can be. In the classical world, you could theoretically have a sound that gets quieter and quieter, infinitely approaching zero, without ever stopping. But in the quantum world, there is a floor. There is a bottom step. You can reduce the energy of a vibration until you have exactly one phonon left. If you remove that last phonon, you do not have a smaller sound. You have silence. You have the quantum ground state. This realization that sound is made of particles changes how we look at the very air in front of our faces. It transforms the empty space of your quiet room into a bustling, pixelated reality. The silence you hear is not an absence. It is a state where the phonon count has dropped low, but the potential for sound, the lattice of the air, remains. Scientists have actually managed to isolate these ghost particles. In experiments conducted at research centers like the University of Chicago and the Max Planck Institute, physicists have been able to manipulate individual phonons. They have built tiny mechanical drums, microscopic devices that vibrate at incredibly high frequencies, and they have cooled them down to temperatures near absolute zero. By removing the thermal noise, the chaotic jiggling of heat, they have been able to listen to the quantum nature of sound. They have seen sound waves behaving like particles. They have split a phonon in two, observing it in a state of superposition where it exists in two places at once. Imagine that. A single unit of sound, a single whisper of the cosmos, existing in two places simultaneously. It defies our intuition. It defies the logic of the everyday world where a sound is here or there. But in the quantum realm, the rules of location blur. Sound becomes a ghost that can walk through walls. This discovery bridges the gap between the ethereal world of light and the heavy world of matter. For a long time, we thought of light and sound as opposites. Light can travel through a vacuum. Sound needs a medium. Light is a transverse wave. Sound is a longitudinal wave. But at the quantum level, they begin to look like cousins. Photons and phonons. Both are bosons. Both carry energy in discrete packets. Both follow the strange, probabilistic laws of quantum mechanics. So, when we ask what is sound made of, the answer is not just moving air. The answer is that sound is made of math. It is made of discrete, quantized excitations of the cosmic fabric. It is made of phonons. As we sit in our quiet room, listening to the silence, we can now visualize it differently. We are not sitting in an empty void. We are sitting in a field of potential. The air molecules around us are like a vast three-dimensional instrument, a harp with billions of strings. Most of the time, those strings are vibrating chaotically with heat, a noise we have learned to ignore. But when a true sound cuts through, a voice, a note, a clap, it is a stream of phonons, a flock of invisible birds flying through the lattice of the air, carrying energy from one place to another in precise, countable bundles. The universe is granular. It is pixelated. And this granularity extends to the very voice of nature itself. We are living in a digital reality, not an analog one, where even the slide of a cello is actually a cascade of tiny, discrete quantum jumps. But this is just the beginning of our journey. If sound is a particle, does it have mass? Does it have gravity? Can sound fall? Can sound be frozen? As we peel back this first layer of the mystery, we find that the phonon is merely the doorway to a much stranger room. We have stepped off the smooth beach and onto the jagged sands of the quantum shore. The ocean of air is behind us, and ahead lies the strange, silent, and vibrating landscape of the subatomic world. In the next chapter, we will ask a question that seems impossible. If sound is a particle, can it be destroyed? Or does the voice of the universe echo forever in the quantum foam? We will explore the death of a phonon, and we will discover that in the quantum world, nothing ever truly disappears without a trace. The silence is deeper than we thought, but it is also more alive than we could have ever imagined. Have you ever shouted into a vast empty canyon and waited for the echo to return? You throw your voice against the stone walls, and for a moment the canyon speaks back to you. It mimics your shout, softer, perhaps a little distorted, a ghostly repetition of your own existence. But then the echo fades. The second repetition is quieter than the first. The third is barely a whisper. And eventually, there is silence. Where did the sound go? When the last ripple of your voice vanished from the air, did it simply cease to exist? Did the energy that you poured into that shout evaporate into nothingness? Or is it still there, hiding in the invisible fabric of the world, transformed into something else? We tend to think of silence as an ending. We think of the quiet room as a place where the story has stopped. But in the quantum universe, nothing ever truly stops. The disappearance of sound is not a death. It is a transformation. It is a masquerade. And to understand where the ghost particles of sound go when they die, we must look deeper into the material world that hosts them. We must look at the trembling, shivering, breathing nature of solid matter itself. In the previous chapter, we discovered that sound is not a smooth wave, but a stream of discrete packets of energy called phonons. We learned that the smoothness of a melody is an illusion created by the sheer number of these tiny particles. But a phonon is a strange creature. It is what physicists call a quasi-particle. This prefix, quasi, is not an insult. It does not mean fake. It means dependent. A photon of light is a fundamental particle. It can travel through the deepest, emptiest voids of the universe for billions of years without ever touching another atom. Light is a lonely traveler. It is independent. It carries its own existence within itself. You can have light in a vacuum. You can have light in the nothingness between galaxies. But a phonon is a creature of community. A phonon cannot exist in emptiness. It requires a medium. It requires a lattice. It is the collective movement of atoms, a synchronized dance of matter. Without the atoms to dance, there is no dance. This is why space is silent. There are no bridges for the phonon to cross. There is no community of atoms to pass the message along. This dependency makes the phonon incredibly special. It means that sound is an intimate phenomenon. It is a relationship between atoms. It is the way one part of the universe touches another part. Let us visualize this relationship. Imagine a block of iron. To your eyes, it is a cold, gray, solid object. It sits heavy in your hand, unmoving, unchanging. But If you could shrink yourself down to the size of a nanometer and step inside that block of iron, you would find yourself in a vast architectural wonder. You would see the atoms of iron arranged in a perfect crystalline grid, extending in every direction like the columns of an infinite cathedral. These atoms are not floating freely. They are bound to each other by strong forces, electromagnetic bonds, that act like stiff springs. Everything in this cathedral is vibrating. Even if the iron is sitting in a freezing cold room, the atoms are shivering. They are jiggling back and forth against their springs, a constant restless motion. This is the thermal energy of the block. This is its heat. Now, imagine you strike the side of the iron block with a hammer. You are introducing a massive amount of new energy into this cathedral. You are pushing the atoms on the edge. This push compresses the springs. The first row of atoms lurches forward, compressing the springs between them and the second row. The second row feels this push and lurches forward, compressing the springs to the third row. This wave of compression travels through the lattice at thousands of miles per hour. This is the sound wave. This is the stream of phonons marching through the cathedral. But here is where the death of sound happens. As these phonons travel, they interact, they collide. In the perfect world of classical physics, a wave could travel forever if there was no friction. But in the quantum world, the lattice is not perfect. There are defects. There are missing atoms. There are isotopes with slightly different masses. And most importantly, there are other phonons. The thermal jiggling of the atoms, the heat, is itself a chaotic sea of phonons. We call these thermal phonons. They are random, disorganized vibrations. The sound wave you created with the hammer is a stream of coherent phonons, organized, disciplined, marching in step. As your organized army of sound phonons travels through the iron, it encounters the chaotic crowd of thermal phonons. They crash into each other. They scatter. The organized energy of your sound wave gets broken up. The disciplined march turns into a chaotic scramble. The energy is not lost. The first law of thermodynamics assures us that energy cannot be created or destroyed, but it is randomized. The ordered motion of sound becomes the disordered motion of heat. Your voice, when it fades in the room, does not vanish. It warms the air. The shout in the canyon warms the stone walls. The energy of the sound is absorbed by the lattice, causing the atoms to jiggle just a little bit faster, just a little bit more chaotically. The phonon of sound dies and is reincarnated as a tiny fraction of a degree of temperature. This is the ultimate fate of all sound in the universe. It is a one-way journey from order to chaos, from song to warmth. The silence you hear after the echo fades is actually the sound of the universe getting slightly warmer. This connection between sound and heat is profound. In fact, in the mathematics of quantum mechanics, they are described by the same physics. Heat is just sound that has lost its melody. It is sound that has forgotten its song. But let us go deeper. Let us go colder. What if we could remove the heat? What if we could take that block of iron and cool it down, removing the thermal phonons one by one? We lower the temperature to freezing, then to the temperature of liquid nitrogen, then to the temperature of deep space, 3 degrees above absolute zero. Then finally, we approach the theoretical limit, absolute zero, 0 Kelvin, minus 459.67 degrees Fahrenheit. At this temperature, classical physics tells us that all motion should stop. The atoms should freeze in place. The springs should be still. The cathedral of the lattice should be perfectly silent. A frozen graveyard of matter. In a universe governed purely by classical mechanics, Absolute zero is the death of all vibration. It is the end of the phonon. But we do not live in a classical universe. We live in a quantum one. And the quantum laws, specifically the Heisenberg uncertainty principle, forbid total stillness. The principle states that you cannot know both the position and the momentum of a particle with perfect precision. If an atom were to stop moving completely at absolute zero, we would know exactly where it is, its position, and exactly how fast it is moving, zero. This would violate the fundamental laws of reality. Nature does not allow it. So, even at absolute zero, even when all the thermal heat has been sucked away, the atoms continue to move. They continue to shiver with a faint, ghostly vibration. This is called zero-point motion. It is the irreducible energy of existence. It is the hum that never ends. Even in the deepest, coldest silence of the most perfect vacuum or the coldest crystal, there is still a vibration. There are still virtual phonons popping in and out of existence, born from the uncertainty of the vacuum itself. This means that silence, true silence, is physically impossible. To exist is to vibrate. To be is to make a sound, however faint. The universe, at its most fundamental level, is a choir that cannot stop singing, even when the lights go out, even when the heat dies, even when the stars fade. The fabric of reality itself is restless. This realization changes our perception of the void. We often think of the material world as solid and static, but quantum mechanics reveals it to be a shivering ocean of energy. The ground beneath your feet, the chair you are sitting on, the very bones in your body, they are all teeming with phonons. They are all transmitting sound waves constantly, a cacophony of quantum whispers that we are too large and too deaf to hear. And these phonons do not just carry sound and heat. They carry the glue that holds the world together. The reason the iron block is solid, the reason it does not crumble into dust, is partially due to the exchange of phonons between atoms. Just as the exchange of photons creates the electromagnetic force that attracts electrons to protons, the exchange of phonons mediates the forces between atoms in a lattice. Sound is not just something that happens to matter. In a way, it is what makes matter what it is. It is the conversation that atoms hold with one another to agree on being a solid object. If you were to somehow stop the exchange of phonons, if you were to truly silence the lattice, the material might cease to be a material. It might lose its cohesion. The solidity of the world relies on its constant vibration. Stability requires movement. Silence is structural collapse. As we contemplate this, we must ask ourselves another question. We know that sound carries energy. We know that sound can turn into heat. We know that Einstein taught us that energy equals mass times the speed of light squared, E as equal $. If sound is energy, and energy is equivalent to mass, does that mean sound has weight? When you sing a lullaby to a child, does the air in the room get heavier? When a thunderstorm rolls through a valley, does the gravity of the valley increase? Does a hard drive full of music weigh more than an empty one? For decades, physicists believed the answer was no. Phonons were considered massless quasi-particles. They carried momentum, yes, but they were thought to be weightless, like shadows moving across a wall. But in recent years, theoretical physics has thrown a curveball. New calculations suggest that sound waves might, in fact, carry mass. Not a lot, a tiny, almost unmeasurable amount. But not zero. This leads us to a mind-bending possibility. If sound has mass, then sound falls. If you speak, your words are pulled downward by gravity. A shout directed at the sky travels slightly slower than a shout directed at the ground. The phonons are affected by the curvature of space-time just like planets and stars. Imagine the implications of heavy sound. Imagine a star quaking with a massive explosion. The sound waves ripples through the star's interior. If those waves carry mass, they are moving the star's own gravity around. They are shifting the balance of the celestial object. In the next chapter, we will leave the solid lattice of the iron block and venture into the strange world of negative mass. We will ask if sound can fall upwards. We will explore the theoretical possibility that phonons can behave like anti-gravity, pushing against the pull of the Earth. We will dive into the fluid dynamics of the quantum world, where sound flows without friction, creating a superfluid that defies the laws of the classical world. We are just beginning to hear the true song of the universe. The silence is not empty. It is heavy. It is moving. And it is waiting for us to listen closer. Have you ever dropped a stone into a well and waited for the splash? You watch the stone fall, pulled by the invisible, relentless hand of gravity. It accelerates, tearing through the air until it strikes the water below. We accept this as the fundamental law of our existence. Things fall. Apples fall from trees, rain falls from clouds, and planets fall around stars. Gravity is the great anchor that holds the universe down. But what if I told you that there are things in this world that defy this rule? What if I told you that under the right conditions, in the strange and freezing basement of the universe, a sound can fall upwards? What if a whisper could weigh less than nothing, behaving like a bubble of anti-gravity rising against the pull of the earth? We tend to think of weight as a property of matter, a property of rocks and iron and flesh. We do not think of a song as having weight. We do not think of a scream as being heavy. But as we continue our journey into the quantum nature of sound, we find that the rules of the classical world are not just broken, they are inverted. The phonon, that ghostly particle of vibration, has secrets that challenge our understanding of mass itself. We are standing on the edge of a new frontier, looking into a liquid that flows without friction and a sound that travels without dying. This is the world of superfluids and negative mass. If you are finding peace in these strange corners of the cosmos, and if you enjoy unraveling the mysteries of reality with us, please consider subscribing to the channel. I am Walter, the Explorer, and I am grateful to be your companion in this quiet dark. Currently, 73% of the wonderful people traveling on this journey have not yet subscribed. By joining us, you help us bring more of these contemplative stories to life, and you ensure that we can keep exploring the universe together. Thank you for your curiosity. Now, let us return to the weight of the whisper. To understand how a sound could possibly float against gravity, we must first revisit the relationship between energy and mass. In the year 1905, Albert Einstein gave the world an equation that would change history. E equals mc squared. Energy equals mass times the speed of light squared. This simple, elegant equation tells us that energy and mass are two sides of the same coin. They are interchangeable. If you heat up a cup of coffee, you are adding thermal energy to it, and therefore, that cup of coffee actually weighs slightly more than a cold cup. The difference is infinitesimally small, too small for any bathroom scale to measure, but it is real. If sound is energy, and we know that it is, then sound must have a mass equivalent. When a phonon travels through a crystal lattice, it carries energy. Therefore, in the strictest sense of general relativity, a phonon should feel the pull of gravity. A sound wave traveling horizontally across a vast distance should eventually droop towards the ground, just like a thrown baseball. A sound wave traveling downward should speed up, gaining momentum from the Earth's pull. For decades, this was a theoretical curiosity. The mass of a phonon was assumed to be so tiny, so negligible, that it could be ignored. Physicists treated sound as effectively massless, but in recent years, theoretical physicists have looked closer at the equations. They have looked at how sound waves interact with the medium they travel through, and they have found something startling. When a sound wave moves through a fluid, like water or air, it compresses the fluid. It squeezes the atoms closer together. In that moment of compression, the density increases. But sound is a wave. For every compression, there is a rarefaction, a stretching out. In the stretched regions, the density decreases. In a perfect, idealized world, these two effects would cancel each other out. The mass added by the compression would be exactly equal to the mass subtracted by the rarefaction. The net mass transported by the sound wave would be zero. But the universe is not linear. The relationship between pressure and density is not a straight line. It is curved. This means that the compression is slightly harder to achieve than the rarefaction. The balance is not perfect. When you do the math, the complex, nonlinear math of fluid dynamics, you discover that the sound wave actually carries a tiny amount of mass with it. But here is the twist. Here is the moment where the quantum world smiles at us with a riddle. In certain materials and under certain conditions, this effective mass can be negative. Imagine a bubble rising in a glass of soda. Gravity is pulling everything down, the glass, the soda, the air. But the bubble rises. Why? It rises because it is less dense than the fluid around it. It is buoyant. In the language of physics, it behaves as if it has negative mass relative to the fluid. It moves opposite to the gravitational field. Recent calculations suggest that phonons, the particles of sound, can behave exactly like these bubbles. In a gravitational field, a phonon in certain liquids might float. If you were to shout downwards into a deep well filled with such a liquid, your voice would fight against gravity. It would try to rise back up to you. The sound would carry a negative gravitational mass. This concept of negative mass is one of the most exotic ideas in physics. It implies that if you were to push the particle, it would move towards you, not away from you. While we have not yet built a sound levitator based on this principle, the mathematics suggests that sound is far more physical, far more tangible than we ever suspected. It is not just a pattern. It is a physical object that interacts with the gravity of the earth. But to truly see sound behaving as a particle, to see it stripped of all the messy friction of the everyday world, we must go to a place where friction does not exist. We must go to the world of the superfluid. Imagine a liquid that never stops flowing. Imagine a cup of coffee that, if you stirred it once, would continue to swirl for 1,000 years, never slowing down, never losing energy to heat. This sounds like magic, but it is real. It is called superfluid helium. To find it, we must return to the deep cold. We must take helium gas, the same gas that fills birthday balloons, and cool it down. At 4.2 degrees Kelvin, just 4 degrees above absolute zero, helium turns into a normal liquid. It looks like water. It is clear, colorless, and it boils. But if we keep cooling it, pumping away the vapor, lowering the pressure, we reach a critical threshold called the lambda point. At 2.17 degrees Kelvin, at this precise temperature, a transformation occurs that is as dramatic as water turning into ice, but far stranger. The helium stops boiling. The surface becomes perfectly, eerily still. It has become a superfluid. In this state, the atoms of helium lose their individuality. They enter a state of matter called a Bose-Einstein condensate. In our ordinary world, every atom is a separate entity, like a person in a crowd. But in a Bose-Einstein condensate, the atoms overlap, their quantum wave functions merge. They become a single, giant quantum object. The billions of atoms in the cup act as one. They are no longer a crowd. They are a choir singing a single, perfect note. And because they move as one, there is no friction. There is no viscosity. Viscosity is the thickness of a liquid, the resistance it has to flowing. Honey has high viscosity. Water has low viscosity. Superfluid helium has zero viscosity. If you put superfluid helium in a cup, it will do something that looks like a ghost story. It will climb the walls. A thin film of helium, just a few atoms thick, will creep up the side of the cup, defying gravity, flow over the rim, and drip down the outside until the cup is empty. It is a liquid that refuses to be contained. Now, imagine sending a sound into this magical liquid. In the previous chapter, we talked about how sound dies by turning into heat, how organized phonons scatter off thermal phonons. But in a superfluid, at temperatures near absolute zero, there are almost no thermal phonons. The liquid is pure. It is perfect. A phonon traveling through superfluid helium finds itself in a paradise. It can travel without scattering. It can flow without dying. Sound in a superfluid can theoretically travel forever. But the superfluid has another surprise for us. In this strange quantum fluid, sound splits into two. If you send a pulse of heat into the liquid, it does not diffuse slowly like it does in water or iron. In normal matter, heat spreads out like a drop of ink in water. But in a superfluid, heat moves as a wave. It moves like sound. Physicists call this second sound. Imagine that. In this quantum world, you can hear heat. If you had a heater oscillating in a bath of superfluid helium, it would emit waves of temperature that travel at a specific speed, preserving their shape, bouncing off walls, interfering with each other just like sound waves. The distinction between thermal energy and acoustic energy blurs. The random jiggling of heat becomes the organized marching of the second sound. And deeper still, within the mathematical description of this fluid, lies a creature even stranger than the phonon. It is called the roton. In the 1940s, the great physicist Lev Landau was trying to understand the behavior of superfluids. He realized that phonons alone could not explain everything. He proposed that there must be another type of excitation, another type of particle in the liquid. He called it a roton. A roton is a ghost of rotation. It is a microscopic vortex, a tiny tornado of quantum fluid. But it behaves like a particle. It carries momentum. It carries energy. And it is intimately connected to sound. In fact, if you look at the energy of a phonon in a superfluid and increase its momentum, it smoothly transforms into a roton. The roton is the deep end of the sound spectrum. It represents a vibration so energetic, with a wavelength so short, comparable to the distance between atoms, that the sound wave starts to curl up on itself. The longitudinal wave of sound twists into the rotational motion of a vortex. So, in the heart of this freezing, frictionless liquid, sound is not just a wave. It is a shapeshifter. It starts as a long, smooth phonon. As it gains energy, it dips into a strange valley of momentum, becoming a roton, a spinning ghost that haunts the fluid. This tells us that sound is far more complex than a simple pressure wave. At the quantum level, sound is a spectrum of identities. It can be a wave. It can be a particle. It can be a vortex. It can be heat. It can carry negative mass. It can defy gravity. We tend to think of the universe as being made of particles of matter, electrons, quarks, neutrinos. We think of these as the real things, the actors on the stage. And we think of sound as just the applause, just a fleeting byproduct of their movement. But the physics of the superfluid suggests something different. It suggests that the excitations, the phonons and rotons, are just as real as the atoms themselves. They have rules, they have lives, they interact, they can be created and destroyed. In some theories of the universe, this idea is taken to its ultimate extreme. Some physicists ask, what if empty space itself is a kind of superfluid? What if the vacuum of the universe is not empty, but a vast, frictionless ocean of quantum potential? And if that is true, what are we? Are the particles that make up our bodies, the electrons and quarks, actually just phonons and rotons in the superfluid of space-time? Are we just the sound waves of the universe? This is a heavy thought. It suggests that we are not the singers, but the song. We are the vibrations of a deeper, underlying reality that we can never truly touch, only infer from the notes that we are made of. As we leave the laboratory of the superfluid with its creeping liquids and negative mass whispers, we must turn our eyes upwards. We have looked at sound in the solid crystal and sound in the quantum liquid. Now we must look at sound in the void. There is a famous tagline from a movie that says, "In space, no one can hear you scream." We have been told that space is a vacuum and sound cannot travel in a vacuum. Therefore, the universe is silent. But is it? Is the cosmos truly a silent movie? Or is there a hum that permeates the darkness between the stars? In the next chapter, we will travel to the edge of a black hole. We will listen to the deepest note ever sung in the universe, a B-flat that has been playing for 2.5 billion years. We will discover that space is not empty, and it is certainly not quiet. The black hole is singing, and its song is shaping the destiny of millions of stars. The silence of the void is a lie. The universe is loud, if you have the ears to hear it. Title: What is sound made of, according to quantum physics? Chapter 4. There is a line from a famous science fiction movie that has haunted our collective imagination for decades. In space, no one can hear you scream. It is a chilling thought, evoking a universe of absolute, suffocating silence. We have been taught to believe that the cosmos is a vacuum, and because sound requires a medium to travel, like air or water or stone, we assume that the emptiness between the stars is a graveyard of noise. We imagine that if a planet were to explode in the deep dark, it would do so without a whisper. We imagine that the collision of galaxies is a silent ballet, a violent dance performed in a library where speaking is forbidden. But this is a myth. It is a misunderstanding of the texture of reality. The universe is not silent. In fact, if your ears were tuned to the right frequencies, and if you could endure the sheer power of the notes being sung, you would find that the cosmos is roaring, it is humming, it is screaming with a voice so deep and so ancient that it shapes the very destiny of the stars themselves. To understand this cosmic sound, we must first let go of the idea that space is empty. The space between stars in a galaxy and the space between galaxies in a cluster is not a perfect vacuum. It is filled with gas. It is filled with the intra-cluster medium, a soup of particles that is incredibly sparse by human standards. If you were to scoop up a cubic meter of this space, you might only find a few atoms. On Earth, that would be considered a vacuum better than any laboratory could create. But on the scale of the cosmos, spread out over millions of light years, those few atoms add up. They form a tenuous, invisible ocean that connects the islands of galaxies. And just like the air in your room, This ocean can vibrate. It can carry a wave. It can carry a sound. This gas is not cold. It is incredibly hot, heated to temperatures of tens of millions of degrees by the gravitational energy released as the cluster formed. Because it is so hot, it glows. It shines brightly, not in the visible light that our eyes can see, but in high-energy X-rays. And it is through these X-ray eyes that we have discovered the true voice of the void. If you are finding a moment of wonder in this journey through the invisible ocean of the cosmos, and if you wish to continue exploring the secrets of the universe with a community of curious minds, please consider subscribing to the channel. I am Walter, the Explorer, and it is a privilege to share these mysteries with you. Currently, 73% of the travelers listening to these stories have not yet subscribed. Your support helps us chart new paths through the stars and bring the wonders of physics down to Earth. Thank you for listening. Now, let us turn our gaze to the constellation of Perseus and to the monster that lives within it. In the heart of the Perseus galaxy cluster, millions of light years from Earth, there sits a supermassive black hole. It is a beast of unfathomable proportions, similar to the giant we discussed in previous stories at the center of ICLM-01. But this black hole is not sleeping. It is active. It is feeding. And as it feeds, it is singing. For years, astronomers using NASA's Chandra X-ray Observatory noticed something strange in the hot gas surrounding the black hole. They saw ripples. They saw concentric rings spreading out from the center, like the ripples in a pond where a stone has been dropped. These were not tricks of the light. They were physical waves of pressure moving through the hot gas. They were compressions and rarefactions. By definition, they were sound waves. But this is not a sound you could hear. The pitch of a sound is determined by the distance between the waves, the wavelength. A high note has waves that are close together. A low note has waves that are far apart. The sound waves rippling through the Perseus cluster are enormous. The distance between one wave crest and the next is roughly 30,000 light years. To put that in perspective, the entire Milky Way galaxy is only about 100,000 light years across. A single oscillation of this sound wave is almost a third the size of our entire galaxy. Because the wavelength is so long, the frequency is incredibly low. The sound being sung by the black hole is a B-flat. But it is a B-flat that is 57 octaves below middle C. This is a note so deep that the human mind can barely comprehend it. The limit of human hearing is about 20 hertz, 20 cycles per second. This cosmic B-flat has a frequency of 1 cycle every 10 million years. It is a sound that plays out over geological timescales. It is a drone that has been humming for 2.5 billion years, a constant, unwavering note in the darkness. But why is it there? What is creating this titanic music? The answer lies in the violence of the black hole itself. As matter falls towards the event horizon, not all of it is consumed. Some of it is accelerated by magnetic fields and blasted back out into space in the form of relativistic jets, streams of particles moving at nearly the speed of light. These jets are like fire hoses of unimaginable power. They slam into the surrounding intracluster gas, carving out enormous cavities. These cavities are essentially bubbles of nothingness blown into the hot atmosphere of the cluster. As the jets push against the gas, they create pressure waves. The bubbles expand and contract. They pulse. And just as a beating drum skin pushes the air to create a sound, the beating jets of the black hole push the gas to create these galactic ripples. The black hole is an instrument. It is a pipe organ the size of a solar system, playing a note that travels for millions of miles. But this sound is not just a curiosity. It is not just cosmic background noise. It is a mechanism of survival for the galaxy itself. This brings us back to the connection between sound and heat that we explored in the previous chapter. We learned that sound, when it dies, turns into heat. The phonons scatter and randomize, raising the temperature of the medium. In the Perseus cluster and in giants like IC 1101, this conversion of sound to heat is crucial. The gas in these clusters is constantly trying to cool down. As it emits X-rays, it loses energy. If left alone, the gas would cool, condense, and fall inward toward the center of the galaxy. This rain of cold gas would trigger a massive burst of star formation. Billions of new stars would ignite, changing the structure of the galaxy forever. But we do not see this massive starburst. The galaxies remain relatively quiet and stable, populated by old red stars. Why? Because the black hole is acting as a thermostat. The sound waves generated by the black hole carry energy away from the center and deposit it into the gas. As the ripples travel outwards, they fade. The energy of the sound is absorbed by the gas, keeping it hot. The song of the black hole is heating the universe around it. It prevents the gas from cooling. It prevents the gas from collapsing. It stops the birth of new stars. Think about the profundity of this. The structure of the universe, the reason these galaxies look the way they do, is determined by sound. A single, low, monotonous note, played for billions of years, provides the energy balance that keeps the galaxy alive. If the black hole were to stop singing, the gas would cool, the galaxy would change, and the delicate equilibrium would be lost. The silence would be a catastrophe. This phenomenon is not unique to Perseus. We see evidence of it in many galaxy clusters, including the environment around IC 1101. We see the cavities, we see the bubbles, we see the evidence of past outbursts, where the black hole was much more active than it is today. These giant elliptical galaxies are sculpted by the acoustics of their own central monsters. So, sound in space is not only real, it is a dominant force. It carries energy, it transports heat, it regulates the life cycle of stars. The phonons we discussed earlier, those tiny quantized packets of vibration, are marching across distances that defy the human imagination, carrying the message of the black hole to the furthest reaches of the cluster. But there is another sound in the universe, one that is even older and more pervasive than the song of a black hole. It is a sound that comes from everywhere and nowhere at once. It is a relic of the very beginning of time. If we could look back, far back, to the moment when the universe was just a baby, we would find that the entire cosmos was once a single, vast instrument. The early universe was a hot, dense soup of plasma, a fluid of light and matter coupled together. In that primordial soup, sound waves traveled just as they do in the air today. These were not sounds created by black holes or stars, for none existed yet. These were the sounds of the Big Bang itself. These primordial sound waves were created by tiny quantum fluctuations, random jitters in the energy density of the infant universe. Gravity tried to pull the matter together, while the pressure of light tried to push it apart. This tug of war created oscillations. It created sound. The universe rang like a bell. We cannot hear this sound directly anymore. The plasma has long since cooled and thinned, but we can see the echoes. We can see the frozen sound. When the universe cooled enough for atoms to form, the light broke free and traveled across the cosmos to reach us today. We call this the cosmic microwave background radiation. When we look at a map of this radiation, we see tiny spots of slightly higher and lower temperatures. These spots are the imprints of those ancient sound waves. They are the crests and troughs of the primordial symphony. The galaxies we see today, the vast clusters, the long filaments of the cosmic web, formed where those sound waves bunched matter together. You are living in a universe that is structured by sound. The distribution of galaxies in the sky is a visual representation of the acoustic harmonics of the Big Bang. We are the solidified echo of the first cry of creation. The investigation of sound has taken us from the quiet room to the quantum crystal, from the superfluid liquid to the singing black hole, and finally back to the birth of time. We have seen that sound is a particle. We have seen that it is heat. We have seen that it is a sculptor of galaxies. But there is one final frontier we must cross. We have talked about sound as a physical thing, an external phenomenon. But what about the sound that happens inside? What about the mechanism of hearing itself? How does a quantum vibration in the air become a spark of consciousness in the mind? Is the biology of hearing also quantum? In the next chapter, we will shrink down once again, not to the atomic lattice, but to the delicate, wet machinery of the human ear. We will explore the Brownian motion that sets the limit of our hearing. We will ask if our ears are sensitive enough to hear the quantum jitter of air molecules. And we will discover that evolution has pushed our senses to the very edge of what the laws of physics allow. We are walking biological quantum detectors, tuned to the whisper of the world. Have you ever laid your head on a pillow in the dead of night and listened to the rhythm of your own existence? You hear the slow, rhythmic thud of your heart, a drum beating deep within the cage of your chest. You hear the high-pitched whine of your nervous system, the electricity of your brain humming like a distant wire. We tend to think of hearing as a passive act, as if the ears are simply open windows through which the world flows. But hearing is not passive. It is an act of aggressive, miraculous detection. It is the ability to capture a ghost. When a sound wave reaches you, whether it is the roar of a jet engine or the rustle of a dry leaf, it has already traveled through the chaotic ocean of the air, surviving collisions with billions of molecules. It arrives at the side of your head as a faint, dying tremor of pressure. And yet, your body is built to catch this tremor. It is built to amplify it, to translate it, and to turn the mechanical motion of the universe into the electrical spark of a thought. We have spent this journey exploring the physics of sound outside of us, in the crystal, in the superfluid, in the black hole. But now, we must turn the lens inward. We must look at the machine that allows us to perceive the symphony. We must ask, how sensitive is the human ear? And when we answer this question, we find that we are standing on a razor's edge. We are balanced precariously between the world of human meaning and the terrifying, chaotic roar of the quantum underworld. To understand the miracle of hearing, we must first appreciate the scale of the energy involved. A whisper is not a strong thing. The amount of energy contained in a quiet conversation, if it could be perfectly captured and stored for 100 years, would barely be enough to heat a single cup of coffee. The ear is an instrument designed to detect the flutter of a butterfly's wing from across a room. If you are finding a moment of calm in this exploration of our own biology, and if you wish to continue unraveling the mysteries of the universe with us, please consider subscribing to the channel. I am Walter, the Explorer, and it is a joy to walk this path of discovery with you. Currently, 73% of the curious souls listening to these stories have not yet subscribed. Your support helps us dive deeper into the wonders of science and keeps this community of explorers growing. Thank you for lending us your ears. Now, let us descend into the spiraling cathedral of the inner ear. The journey of a sound wave into your mind begins at the eardrum, a thin, taut membrane of skin. When the pressure wave hits it, it vibrates. This vibration is passed through 3 tiny bones, the hammer, the anvil, and the stirrup, the smallest bones in the human body. These bones act as a lever system, amplifying the force of the faint air pressure and focusing it onto a small window that leads to the inner ear, the cochlea. The cochlea is a masterpiece of biological engineering. It is a fluid-filled chamber coiled like a snail shell. Inside this chamber, there is a membrane lined with thousands of tiny hair cells. These are not hairs in the sense of the hair on your head. They are microscopic bundles of protein called stereocilia. They are the antennae of the mind. They stick up into the fluid of the cochlea, like tall grass in a stream. When the sound wave pushes on the fluid moves. The wave travels through the liquid, causing the membrane to ripple. And as the membrane ripples, the tiny hairs bend. This bending is the critical moment. When a hair cell bends, it opens a tiny molecular gate, allowing ions to rush in and creating an electrical signal that travels to the brain. This is the moment where the physical motion of the universe becomes the subjective experience of hearing. But how much do these hairs actually move? This is where the physics becomes staggering. For a sound at the very threshold of human hearing, the quietest sound a healthy young person can detect, defined as 0 decibels, the vibration of the air is almost unimaginably small. When this faint pressure wave travels through the ear and pushes on the hair cells, the amount of displacement, the distance the hair bends, is less than the diameter of a single hydrogen atom. Let that sink in. A hydrogen atom is the smallest object in the universe that can still be called an atom. It is the fundamental building block of matter, and your ear can detect a movement smaller than that. If you were to scale the hair bundle up to the size of the Eiffel Tower, the movement required to detect a whisper would be equivalent to the tower swaying by less than the width of a piece of paper. This extreme sensitivity places the human ear at the very limit of what is physically possible. We are operating at the boundaries of the laws of physics. If our ears were any more sensitive, even by a tiny fraction, we would not hear more of the world. We would hear the world falling apart. This brings us to the phenomenon known as Brownian motion. In the year 1827, a botanist named Robert Brown was looking through a microscope at pollen grains suspended in water. He noticed something strange. The pollen grains were not sitting still. They were jittering. They were dancing around in a chaotic, random path as if they were alive. But they were not alive. Brown could not explain it. It took nearly 80 years for Albert Einstein, in one of his Miracle Year papers of 1905, to explain the mystery. Einstein realized that the pollen grains were being bombarded by the invisible water molecules. The water itself was not a still fluid. It was a chaotic storm of atoms crashing into each other and into the pollen grains billions of times a second. The jittering of the pollen was the visible evidence of the atomic world. It was the thermal noise of the liquid. The air around you is doing the same thing. The molecules of nitrogen and oxygen are zipping around at hundreds of miles per hour, crashing into everything they touch. They are crashing into your skin. They are crashing into your eyes. And, crucially, They are crashing into your eardrums. Every second, billions of air molecules bombard your eardrum. This bombardment is random. It creates a fluctuating pressure. It creates a noise. This is the sound of heat. This is the sound of the atmosphere boiling. If your ears were slightly more sensitive, if evolution had pushed the limit just a little bit further, you would hear this constant bombardment. You would hear a permanent, unceasing hiss. It would sound like white noise, like a television tuned to a dead channel, playing at a volume that you could never turn down. The roar of the air molecules would drown out the rustle of leaves, the breath of a loved one, and the silence of the night. You would be trapped in a world of constant acoustic chaos. The peace of a quiet room would be impossible, because the air in the room is not quiet at the atomic level. Evolution, in its ancient wisdom, has tuned our ears to be exactly as sensitive as they can be without crossing this line. We are tuned to the thermal limit. The threshold of human hearing sits just above the noise floor of Brownian motion. We possess the maximum possible sensitivity that is useful. Any more sensitivity would be a curse. This realization changes the way we think about silence. Silence is not an objective property of the universe. The universe is never silent. The air is always screaming with thermal energy. Silence is a construction of our biology. It is a filter. Our brain and our ears have evolved to ignore the constant roar of the quantum storm so that we can focus on the signals that matter, the crack of a twig, the cry of a baby, the thunder of a storm. We are shielded from the true chaos of reality. We live in a protected bubble of perception, where the air feels smooth and the silence feels empty. But just outside that bubble, less than an atomic width away, the universe is a violent, crashing ocean of particles. This connects us back to the phonon, the thermal energy of the air. The heat that causes the molecules to crash into your eardrum is a sea of incoherent thermal phonons. Your ear is designed to ignore these random phonons and only detect the coherent, organized phonons of a sound wave. We are biological filters, separating the signal from the noise, the music from the heat. But there is another layer to this mystery. The hair cells in your ear are not just passive detectors. They are active amplifiers. The cochlea is not just a microphone. It is a synthesizer. Inside the quiet dark of your inner ear, the hair cells are constantly twitching. They are injecting energy into the sound wave to amplify it. This process is so active that sometimes the ear actually makes sound. In a quiet room, healthy ears emit faint whistles and hums called autoacoustic emissions. Your ears are singing back to the world. This active amplification is powered by biological motors, tiny proteins that crawl along the structure of the cell. These motors are subject to the same thermal noise, the same Brownian chaos. And yet, somehow, they operate with a precision that rivals our best technology. They can distinguish between two notes that differ in frequency by a fraction of a percent. They can detect a timing difference between the left ear and the right ear of just a few microseconds. How does biology achieve this quantum-level precision in a warm, wet, noisy environment? Some physicists believe that the ear might be using quantum coherence, the same weird physics that allows superconductors to flow without resistance, to enhance its sensitivity. This is the emerging field of quantum biology. The idea is that life, over billions of years of evolution, might have learned to harness the strange rules of the quantum world. Just as plants might use quantum coherence to harvest sunlight in photosynthesis, our ears might be using quantum tricks to capture the faintest whispers of the air. We are not just observing the quantum world. We might be made of it. We might be quantum machines walking through a classical landscape. So, when you sit in that quiet room and hear the blood rushing in your ears, you are hearing the machinery of life keeping you alive. But you are also hearing the silence that protects you from the roar of the atoms. You are hearing the boundary between the macro world of human experience and the micro world of thermal chaos. This boundary is where we live. We exist in the narrow band of tranquility between the quantum storm and the cosmic void. And our senses are the guardians of that tranquility. But this leads us to a deeper, more philosophical question. If our ears filter out the true noise of the universe, and if our eyes can only see a tiny slice of the electromagnetic spectrum, then how much of reality are we actually perceiving? Is the world we see and hear the real world? Or is it just a user-friendly interface designed by evolution to keep us sane? And if sound requires a listener, if the vibration of the air only becomes a sound when it triggers an electrical spark in a brain, then does a falling tree make a sound if no one is there to hear it? This is the ancient koan. But in the light of quantum mechanics, it becomes a question about the nature of reality itself. It becomes a question about the observer. In the next chapter, we will leave the anatomy of the ear and enter the architecture of the mind. We will explore the measurement problem of quantum mechanics. We will ask if the act of hearing a sound actually changes the sound. Does the universe wait for us to listen before it decides what note to play? We will dive into the strange relationship between consciousness and the physical world, and we will discover that the listener is just as important as the song. The journey continues inward, past the eardrum, past the cochlea, and into the mysterious electrical storm of the human consciousness. There is a question that has echoed through the halls of philosophy for centuries, a riddle that seems simple on the surface but hides a terrifying depth beneath its words. If a tree falls in a forest and no one is around to hear it, does it make a sound? We have all heard this question. We have all smiled at it, perhaps dismissing it as a semantic game, a trick of language. We tell ourselves that, of course, it makes a sound. The tree is heavy, the ground is hard, the collision releases energy, the air is pushed. The waves ripple out through the ancient woods, shaking the leaves and disturbing the birds. The laws of physics do not stop working just because we are not looking. Gravity still pulls, matter still strikes matter, and energy still flows. In our classical intuition, the universe is a machine that runs on its own, a clockwork reality that ticks whether or not there is a witness to watch the gears turn. But as we have journeyed deeper into the quantum nature of the world, past the granular staircase of phonons, through the frictionless flow of the superfluid, and into the roaring silence of the black hole, we have learned that our intuition is often wrong. The universe is not a clockwork machine. It is something far more mysterious. It is a cloud of probability. It is a field of potential. And in this strange, twilight world of quantum mechanics, the answer to the riddle of the tree is not a simple yes. The answer is that, without a listener, the sound might not exist at all. This brings us to the most uncomfortable and profound realization of our journey so far. The universe requires an audience. The sound you hear is not just an event happening to you. It is an event happening with you. You are a co-creator of the reality you perceive. If you are finding a sense of awe in these deep questions, and if you enjoy standing on the precipice of the unknown with a community of fellow explorers. Please consider subscribing to the channel. I am Walter, the Explorer, and it is my great honor to guide you through these mysteries. Currently, 73% of the wonderful people listening to these stories have not yet subscribed. By joining us, you help us continue this quiet journey into the nature of existence, and you ensure that we can keep asking the questions that matter. Thank you for being here. Now, let us step into the lonely forest. To understand why the falling tree might be silent, we must first separate the phenomenon into two parts: the physical wave and the subjective experience. In the language of classical physics, the sound wave is a pressure disturbance in the air. When the tree hits the ground, it compresses the air molecules, creating a sphere of expanding energy. This is a mechanical event. It is objective. It can be measured by a microphone. If we define sound purely as this mechanical wave, then yes, the tree makes a sound. The air vibrates regardless of your presence. But is that vibration sound? A vibration is just a movement of atoms. It is silent. It has no quality of loudness or pitch or timbre. Those are qualities that exist only in the mind. They are what philosophers call qualia, the subjective texture of experience. The air does not know it is loud. The air simply moves. The sound is the translation of that movement into a sensation. It is a magic trick performed by the brain. In this sense, without a brain to perform the trick, there is no sound. There is only silence and wind. However, quantum mechanics takes this philosophical distinction and turns it into a physical crisis. It introduces the measurement problem. In the quantum world, particles like electrons and photons, and yes, phonons, do not exist in definite states until they are measured. Before they are observed, they exist in a superposition of all possible states. An electron is not here or there. It is in a ghostly cloud of being everywhere at once. It is a wave of probability. It is only when we look at it, when we interact with it, when we measure it, that the wave collapses into a single, definite particle. This is the famous paradox of Schrödinger's cat. A cat in a box is both dead and alive until you open the box to check. The act of observation forces the universe to choose a reality. Now, apply this to the tree. The tree is made of atoms. The air is made of atoms. The sound wave is a stream of phonons. If we take quantum mechanics to its ultimate logical conclusion, the falling tree is a quantum event. Until the consequences of that event are measured, the system remains in a superposition. The phonons are in a superposition of states. The energy is a cloud of probability spreading through the forest. Who is the observer? Who collapses the wave? Is it the air molecules? Is it the squirrel in the nearby tree? Is it the microphone we left on the forest floor? Or does it require a conscious mind? This is where physics blurs into metaphysics. Some physicists, like the Nobel laureate Eugene Wigner, proposed that consciousness itself is the fundamental variable that collapses the wave function. In the von Neumann-Wigner interpretation, the physical world remains in a suspended state of unreality until a conscious mind perceives it. If this view is correct, then the falling tree in the lonely forest exists only as a ghostly potential. The crash does not happen in a definite way until the information reaches a mind. The sound wave travels through the woods as a probability distribution, a maybe, until it strikes an eardrum and is converted into a signal that a consciousness can acknowledge. In this radical view, you are the machine that makes the sound real. You are not just hearing the universe, you are finalizing it. But let us step back from the edge of solipsism and look at the more widely accepted view: decoherence. In modern quantum theory, we believe that observation does not necessarily require a human mind. It requires an interaction with the environment. The air molecules themselves are constantly interacting with the tree. The photons of sunlight are bouncing off the falling trunk. These billions of tiny interactions measure the tree constantly. They force the quantum superposition to collapse into a classical reality almost instantly. The forest is watching itself. The air is listening to the tree. So, the tree falls. The wave spreads. The phonons march through the air, collapsing from probability into reality with every collision. The physical sound exists, but the mystery remains in the translation. The mystery remains in the dark theater of your mind. Imagine your brain. It is encased in a thick skull, completely sealed off from the outside world. It sits in total darkness. It sits in total silence. No light ever reaches your visual cortex. No sound waves ever touch your auditory cortex. Your brain floats in a warm, dark, silent bath of fluid. And yet, you see a world of light and color. You hear a world of music and voices. How? The only things that enter your brain are electrical spikes, tiny pulses of voltage traveling along axons. The hair cells in your ear, which we explored in the previous chapter, convert the complex, rich, granular dance of the phonons into a stream of simple electrical clicks. Morse code. Your brain takes this Morse code and paints a reality. It generates the sensation of a low hum or a sharp crack. These sensations are not out there in the forest. They are in here. They are a hallucination that corresponds to reality. The frequency of the B-flat from the black hole is a physical fact. The sound of the B-flat is a mental creation. This leads us to a startling conclusion. The universe is silent. It is utterly, profoundly silent. There is no noise in the cosmos. There is only pressure, vibration, and energy. The concept of noise is a biological invention. It is a user interface that our DNA built to help us navigate the energy waves. We are like sailors on a dark ocean who have built a machine that turns the motion of the waves into music. The ocean is not singing. The machine is singing. We are that machine. This realization should not make you feel isolated. It should make you feel empowered. It means that the beauty of a symphony, the comfort of a whisper, and the awe of a thunderclap are treasures that you bring to the universe. Without you, the universe is just a silent shuffling of atoms. You are the instrument that gives the cosmos its voice. But the rabbit hole goes deeper. If the observer is so crucial to the reality of the sound, can the observer change the sound just by listening? In the quantum world, the answer is yes. This is the quantum Zeno effect. It is possible to freeze a quantum system in its state simply by observing it repeatedly and rapidly. It is the idea that a watched pot never boils. If you measure a quantum system fast enough, you prevent it from evolving. Could this apply to hearing? In a metaphorical sense, our attention shapes what we hear. We know this from the cocktail party effect. In a crowded room, you can focus on a single voice and tune out the rest. Your brain physically suppresses the signals from the other conversations. You are collapsing the auditory chaos into a single stream of meaning. You are choosing which reality to perceive. But in the literal quantum sense, could our hearing affect the phonons themselves? In the previous chapter, we discussed how the ear emits sound, otoacoustic emissions. We are active listeners. We are injecting energy back into the field. This means that every time you hear a sound, you are physically interacting with the source. You are not a passive bucket catching rain. You are a hose spraying water back into the storm. Your listening changes the air. Your presence alters the acoustic field of the room. The observer effect is not just a quantum curiosity. It is a fundamental truth of existence. To know a thing is to touch it. To hear a sound is to change it. There is no such thing as a detached observer. We are entangled with the world we perceive. This word, entanglement, is the key to the next stage of our journey. We have looked at single particles. We have looked at waves. We have looked at the listener. But quantum mechanics tells us that particles can become linked across vast distances, sharing a destiny that defies the speed of light. Can sound be entangled? Can a drum beaten on Earth cause a drum on Mars to vibrate instantly without a wave traveling between them? Can two phonons share a soul? In the next chapter, we will explore the entanglement of sound. We will look at experiments where physicists have managed to entangle two tiny mechanical drums, creating a quantum link between macroscopic objects. We will ask if the vibrations of the universe are all connected in a vast, invisible web. We will discover that the separation between here and there is just another illusion, and that the song of the cosmos might be playing everywhere at once. The silence of the forest is not empty. It is waiting for you, and when you walk into it, you do not just disturb the peace. You create the sound. You are the necessary ingredient. You are the witness that turns the probability of the universe into the reality of the moment. So, the next time you hear a leaf fall, remember, you are doing the work of creation. You are taking the silent, cold energy of a collision and transmuting it into the warm, rich gold of experience. You are the alchemist of the air. And as we prepare to leave the dark theater of the mind and step back out into the entangled web of the cosmos, ask yourself, if I stop listening, does the song stop? Or does it continue in the mind of the universe itself? Have you ever felt a connection to someone so strong that it felt like you were two parts of the same soul? A feeling that when they were in pain, you could feel a shadow pass over your own heart, even if they were thousands of miles away. We often speak of these connections in the language of poetry and love. We talk of invisible threads, of kindred spirits, of vibes that transcend the physical distance between two bodies. We dismiss these feelings as metaphors, as beautiful illusions of the human emotional system. We tell ourselves that in the cold, hard reality of physics, separation is absolute. An object here is distinct from an object there. Space is a barrier that can only be crossed by time and energy. A message must travel. A signal must fly. Nothing is instant. Nothing is truly one. But what if the poets were right and the classical physicists were wrong? What if the universe is not a collection of lonely islands, but a single, vast, shimmering web where distance is just a dream? As we delve deeper into the quantum nature of sound, we arrive at the most mind-bending phenomenon in all of science, entanglement. And we are about to discover that the ghost particles of sound, the phonons, can be linked across the void in a way that defies the very concept of space itself. In the previous chapters, we learned that sound is a particle, a phonon. We learned that it carries mass, that it can turn into heat, and that it requires a listener to collapse into reality. But we have treated these phonons as individual travelers. We have imagined them bouncing around inside a crystal or flying through the air like tiny tennis balls. Now, we must imagine something stranger. Imagine two drums. One is sitting in a laboratory in London. The other is sitting in a laboratory in New York. You strike the drum in London, instantly, faster than the speed of light, faster than any signal could possibly travel. The drum in New York begins to vibrate in perfect harmony. They are not communicating. They are not sending radio waves. They are simply sharing a single existence. They are entangled. This sounds like magic. It sounds like a violation of everything we know about the speed limits of the universe. Albert Einstein himself hated this idea. He called it spooky action at a distance. He believed that physics should be local, that things should only affect their immediate neighbors. But the universe, it turns out, is spooky. And in the quiet, frozen laboratories of the 21st century, scientists have proven that this magic is real. And they have done it with sound. If you are finding comfort in the realization that we are more connected than we think, and if you want to explore the strange unity of the cosmos with us, please consider subscribing to the channel. I am Walter, the Explorer, and I am honored to be your guide through the invisible webs of reality. Currently, 73% of the curious minds traveling with us have not yet subscribed. It helps us bring more of these contemplative stories to you, and it lets us know that you want to keep exploring the universe together. Thank you for being part of this connection. Now, let us enter the world the entangled drums. To understand how sound can be entangled, we must first understand what entanglement is. In the quantum world, when two particles interact in a certain way, they lose their individual identities. They become a single quantum system described by a single mathematical wave function. Even if you separate them by billions of light years, they remain linked. If you measure the spin of one particle and find it to be up, the other particle will instantaneously decide to be down. It is as if they are a pair of dice that always roll, adding up to 7, no matter how far apart they are thrown. For a long time, physicists thought this delicate connection could only exist between tiny, isolated particles like electrons or photons. They thought that big, hot, messy objects like drums or cats or people could never be entangled. The thermal noise, the Brownian motion we discussed earlier, would destroy the delicate quantum link. The chaos of the environment would sever the thread. But in the year 2021, 2 teams of physicists, one at the National Institute of Standards and Technology, NIST, in the United States, and another at the University of New South Wales in Australia, did the impossible. They entangled sound. They built tiny mechanical drums. These were not drums you could play with a stick. They were microscopic membranes of aluminum about the width of a human hair. To a quantum physicist, a human hair is enormous. It contains trillions of atoms. It is a macroscopic object. These drums were placed in a dilution refrigerator and cooled down to near absolute zero, removing the thermal noise, silencing the chaos of the heat. Using microwave pulses, the scientists gently struck these drums. They set them vibrating, but they did it in a way that the vibration of one drum was mathematically linked to the vibration of the other. They created a state where the position of the drumheads was entangled. If drum A was vibrating up, drum B was vibrating down. But here is the catch. Until they measured them, neither drum was vibrating up or down. They were both vibrating in a superposition of both states, and they were sharing that superposition. When the researchers measured the position of one drum, the other drum instantly snapped into the corresponding state. The vibration, the sound, was non-local. The phonon was not in drum A or drum B. The phonon was in both drums at once, a shared ghost of energy that spanned the distance between them. This experiment shattered the boundary between the quantum world and the everyday world. It proved that sound, the collective motion of trillions of atoms, can be a quantum object. It proved that a mechanical vibration, something you could theoretically hear if your ears were small enough, can defy the laws of locality. Think about the implications of this. We usually think of sound as a traveler. It leaves my mouth, travels through the air at 760 miles per hour, and arrives at your ear. It takes time. It crosses space. But entangled sound does not travel. It is. It exists in two places simultaneously. It suggests that the fabric of the universe is capable of holding a vibration that is omnipresent within its own system. This leads us to a profound contemplation of the universe as a whole. If two tiny drums can be entangled, what else can be? When the universe began, in the first fraction of a second of the Big Bang, all matter and energy was compressed into a point smaller than a single atom. Everything that exists today, the stars, the galaxies, the gas clouds, the planets, and the atoms in your body, was once touching. We were all part of the same initial quantum fire. Does that mean that in some deep, fundamental way, everything in the universe is still entangled? Is the cosmic web not just a web of gravity, but a web of quantum connection? If the atoms in your brain were once adjacent to the atoms in a star on the other side of the galaxy, is there a faint, ghostly thread that still connects you? When a star dies, a billion light years away, does a tiny part of you vibrate in sympathy? We cannot send messages through entanglement. The laws of physics, specifically the no communication theorem, forbid us from using this link to send faster than light signals. You cannot use entangled drums to send a Morse code warning to Mars. The correlation is random. You cannot control the outcome of the measurement to encode a bit of information. Nature protects her speed limit. The speed of light remains the supreme law for information. But connection is not the same as communication. The drums are connected, even if they cannot speak. They share a destiny. They share a state. This brings a new meaning to the idea of the music of the spheres. The ancient Greeks believed that the planets and stars moved in a divine harmony, creating a celestial music that humans could not hear. Entanglement suggests a different kind of music, a music where the notes are not sequential, but simultaneous, a music where the orchestra is the entire universe, and the instruments are linked by invisible strings that ignore the vast emptiness of space. Let us return to the room where you are sitting. Look at the objects around you, the chair, the table, the window. They seem separate. There is air between them. There is distance. But if you could look with the eyes of the quantum drums, you might see that the separation is an illusion of scale. The air between you and the window is filled with phonons. We know this. But now we must wonder, are the phonons in the air entangled with the phonons in the glass? Is the vibration of the room a single, complex quantum state that we are only seeing in slices? Maybe the silence you hear is just the sound of a universe that is holding its breath in unison. There is another fascinating aspect to this experiment. The scientists used microwave light to entangle the mechanical sound. They built a bridge between light and sound. They converted a photon into a phonon and back again. This is called quantum transduction. It means that sound and light are not just cousins. They are bilingual. They can speak to each other. They can trade secrets. A quantum computer of the future might use light to send information and sound to process it. The hum of the computer would be a quantum calculation happening in the language of vibrations. We are moving toward a future where we will manipulate sound with the same precision that we manipulate light. We will sculpt the air. We will build networks of entangled drums that span cities, creating a web of sensors so sensitive that they could detect the passage of dark matter. Yes, dark matter. That mysterious, invisible substance that makes up 85% of the matter in the universe. We cannot see it. We cannot touch it. But it has mass. And if it has mass, it can hit things. If a particle of dark matter were to fly through the laboratory and strike one of these entangled drums, it would disturb the entanglement. It would break the symmetry. The sound of the dark matter striking the drum would be detected not by the loudness, but by the loss of the quantum link. We are building ears that can hear the invisible ghost of the cosmos. We are building drums to catch the shadow of the universe. As we ponder this, we realize that our journey has taken us from the simple idea of sound is a wave to sound is a particle, then sound is heat, then sound is a creator of galaxies, and now sound is a non-local quantum ghost. The definitions are dissolving. The boundaries are melting. The universe is becoming more fluid, more connected, and more mysterious the closer we look. But there is one barrier we have not yet challenged. We have talked about sound traveling through materials and sound generated by black holes in gas. We have talked about entangled drums. But what about the fabric of space-time itself? Einstein told us that gravity is a curvature of space-time. When two black holes collide, they send out ripples in this fabric, gravitational waves. Are these waves sound? They vibrate. They have frequency. They carry energy. They travel at a speed. But they do not travel through air. They do not travel through gas. They travel through the vacuum itself. They are the sound of space squeezing and stretching. In the next chapter, we will ask the ultimate question. What is the speed of sound in the vacuum? Does the universe itself have a stiffness? And if gravitational waves are the sound of space-time, can we hear them? We will explore the chirp of colliding black holes that was heard by the LIGO Observatory, a sound that traveled for 1 billion years to ring a bell on Earth. We will discover that we have finally built the ears to hear the universe screaming. The web is tight, the drums are linked, and the whole cosmos is shaking. Imagine a bell. It is not a bell made of bronze or brass. It is not a bell that hangs in a tower or sits on a shelf. It is a bell made of nothing. It is a bell made of emptiness. It is a bell made of the very fabric of reality itself. When you strike a normal bell, the metal vibrates. The atoms push against the air, and the air pushes against your ear. We call this sound. But what happens when you strike the universe? What happens when you take the empty vacuum of space, the stage upon which all the stars and galaxies dance, and you hit it with a hammer made of pure gravity? For centuries, we believed that the vacuum was silent. We believed that space was a passive, static void, a mere container for matter. We thought that if a star exploded in the deep dark, the silence would be absolute because there was no air to carry the scream. But in the year 1916, Albert Einstein gave us a new pair of ears. He told us that space is not empty. He told us that space is a thing. It is a fabric. It can stretch. It can squeeze. It can bend. And if you hit it hard enough, it can ring. This ringing is not sound in the acoustic sense. It is not a pressure wave moving through gas. It is a ripple in the geometry of the universe. It is a wave where space itself expands and contracts. And yet, when we look at the mathematics, when we look at the way these waves behave, they are the sound of gravity. They have frequency. They have amplitude. They travel at a speed. And just like a sound wave tells you about the drum that made it, these gravitational waves tell us about the most violent events in the cosmos. We have spent this journey listening to the air, to crystals, to superfluids. Now, we must listen to the vacuum. We must listen to the chirp of the black hole. If you are finding a moment of awe in the realization that the universe itself is a ringing bell, and if you wish to continue this exploration of the cosmic symphony with us, please consider subscribing to the channel. I am Walter, the explorer, and I am honored to be your companion in the dark. Currently, 73% of the curious minds traveling on this journey have not yet subscribed. By joining us, you help us build a community of listeners who are not afraid of the deep questions, and you ensure that we can keep bringing the wonders of physics to light. Thank you for listening to the universe with me. Now, let us turn our attention to a galaxy far, far away, and to a dance of death that happened 1 billion years ago. In a distant corner of the cosmos, 2 black holes were locked in a gravitational embrace. These were not supermassive monsters like the one in IC 11-1. These were stellar mass black holes, the corpses of giant stars. Each one was about 30 times the mass of our sun, compressed into a sphere only a few hundred miles across. They were orbiting each other, spiraling inward, drawn together by their mutual gravity. As they spiraled, they dragged the fabric of space-time with them. Imagine stirring a thick pot of honey with 2 spoons. The honey swirls and ripples. Space-time is like that honey, but much, much stiffer. As the black holes moved, they sent out waves of gravitational energy. These waves rippled outward at the speed of light, carrying energy away from the binary system. Because they were losing energy, the black holes fell closer together. They spun faster. The waves got stronger. The frequency of the ripples increased. It was a cosmic crescendo. Faster and faster they spun, until they were moving at nearly half the speed of light. And then, in a fraction of a second, they touched. They merged. They became one. In that final moment of collision, the energy released was staggering. For a brief instant, that single merger released more power than all the stars in the observable universe combined. But it was invisible. There was no flash of light. There was no explosion of fire. To the eyes, it was pure darkness. The energy was released entirely as gravitational waves. These waves traveled outward through the universe. They passed through galaxies. They passed through gas clouds. They passed through stars. And for 1 billion years, they traveled through the void, getting weaker and weaker as they spread out, until they reached a small, blue planet orbiting an ordinary yellow star. On September 14th, 2015, those waves washed over the Earth. When a gravitational wave passes through you, it stretches you, it squeezes you. If you were floating in space and a strong wave passed by, you would be stretched tall and thin like a piece of spaghetti, and then squashed short and wide like a pancake. This stretching and squeezing happens to everything, to you, to the Earth, to the atoms themselves. But the effect is tiny. By the time the waves from the black hole merger reached Earth, the amount of stretching was almost zero. It changed the diameter of our planet by less than the width of a proton. How could we possibly hear such a faint whisper? How could we detect a tremor in reality that is smaller than an atomic nucleus? The answer lies in the most sensitive ear ever built by human hands. LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO is not a telescope. It does not look at the sky. It listens to the ground. It consists of 2 giant L-shaped detectors, one in Louisiana and one in Washington State. Each arm of the L is a concrete tunnel 4 kilometers long. Inside the tunnel is a vacuum tube, one of the purest vacuums on Earth. And inside that tube, a laser beam travels back and forth between mirrors. The laser acts as a ruler made of light. It measures the distance between the mirrors with incredible precision. When a gravitational wave passes through the detector, it stretches one arm of the L and squeezes the other. The distance the laser has to travel changes. The light waves go out of sync. When they recombine at the detector, they create an interference pattern. They create a signal. On that September day at 5:51 in the morning, the signal arrived. It hit the detector in Louisiana first, and then, 7 milliseconds later, it hit the detector in Washington. It was a perfect match. The signal started as a low rumble, then quickly rose in pitch and volume, ending in a sharp chirp before cutting off abruptly. This was the sound of the black holes spiraling together, low frequency, and then merging, high frequency, and then settling down into a single quiet object, silence. Scientists took this data, the frequency of the stretching of space, and converted it into sound waves that human ears could hear. They played the chirp. It sounded like a whoop, a short, sliding whistle. It was the most beautiful sound ever heard in the history of physics. It was the voice of gravity. It was the proof that Einstein was right. It was the proof that black holes are real. And it was the proof that space itself is a dynamic, vibrating medium. But let us think about this medium. We know that sound travels through materials. The speed of sound depends on two things: the density of the material and its stiffness. Sound travels faster in water than in air because water is stiffer. It travels faster in steel than in water because steel is stiffer. The stiffer the material, the harder it is to compress, and the faster the wave moves. Gravitational waves travel at the speed of light. This is the cosmic speed limit, roughly 670 million miles per hour. For a wave to travel that fast, the medium it travels through must be incredibly stiff. If we treat space-time as a material, if we treat the vacuum as a solid through which these waves are moving, we can calculate its stiffness. The result is mind-boggling. Space-time is the stiffest material in the universe. It is roughly 10 to the power of 20 times stiffer than steel. This is why we think of space as empty and yielding. We move through it effortlessly. Earth orbits the sun without friction, but that is only because we are moving at low speeds and low energies. To a gravitational wave, space-time is as rigid as a diamond. It is incredibly hard to bend. It takes the collision of black holes, the most violent event possible, to create even a tiny ripple. This stiffness is what holds the universe together. It is the backbone of reality. If space-time were soft, gravity would be chaotic. Planets would wobble. Stars would not form. The rigidity of the vacuum is the silent strength that allows the cosmos to exist. So, when we ask, what is sound made of, we now have a new answer. In the vacuum, sound is made of geometry. It is made of the stretching and squeezing of the distance between points. It is the vibration of the ruler itself. But there is a deeper philosophical implication to LEGO. Before 2015, everything we knew about the universe came from light. We looked at the stars, we looked at galaxies, we looked at the cosmic microwave background. We were astronomers using our eyes. Now we are using our ears. LIGO is a microphone. We have added a new sense to our species. We can now hear events that are invisible. We can hear black holes colliding in the dark. We can hear the interior of a neutron star as it cracks. We can potentially hear the Big Bang itself. There is a theoretical background of gravitational waves called the stochastic background. It is the hum of millions of black hole mergers happening all over the universe, all overlapping into a single chaotic noise. It is the static of the cosmos. LIGO is trying to tune into this static. And beyond LIGO, we are building LISA, the Laser Interferometer Space Antenna. This will be a detector floating in space with arms millions of miles long. It will be able to hear low-frequency gravitational waves, the deep rumbles of supermassive black holes merging at the centers of galaxies. It will hear the B-flat of the Perseus cluster directly. We are no longer deaf. The universe has opened its mouth and spoken to us, and we have built the machine to translate its language. But this brings us back to the vacuum. We have described space-time as a stiff fabric. We have described it as a medium. But is it really empty? If it can ripple, if it can carry energy, if it has stiffness, does it have substance? In quantum field theory, the vacuum is not empty. It is a bubbling soup of virtual particles appearing and disappearing. It is a sea of energy. And this energy, the zero-point energy, is the source of the mass of the universe. If sound is a vibration of matter and gravitational waves are a vibration of space-time, is there a connection? Is the fabric of space-time made of something even more fundamental? Some physicists propose that space-time itself is emerged from quantum entanglement. They call it it from qubit. The idea is that the geometry of the universe, the stiffness, the distance, the shape, is created by the entanglement of quantum information. Space-time is not the stage. It is the actors holding hands. If this is true, then gravitational waves are ripples in the web of entanglement. They are the sound of the quantum connection stretching and breaking. The chirp of the black hole is the sound of quantum information being scrambled and reorganized. As we stand in the laboratory of LIGO, listening to the whoop of a billion-year-old collision, we realize that the silence of the night is an illusion on every level. The air is crashing with thermal noise. The crystals are shivering with phonons. The vacuum is trembling with gravitational waves. There is no place in the universe where there is truly nothing. There is no place where there is truly silence. The symphony is everywhere. It is in the air. It is in the ground. It is in the empty space between the stars. And you, with your ears and your mind, are the point where the symphony becomes conscious. You are the universe listening to itself. But what happens when the sound gets too loud? What happens when the energy density of the sound becomes so high that it breaks the laws of physics? In the next chapter, we will explore the sonic black hole. We will look at experiments where scientists have created dumb holes, acoustic black holes, in the laboratory using sound waves and fluids. We will ask if sound can be trapped. We will ask if a scream can be so loud that it creates an event horizon from which no echo can escape. We will discover that sound and gravity are mirrors of each other, and that by studying the phonon, we might unlock the secrets of Hawking radiation and the ultimate fate of the universe. The bell has rung, the wave has passed, but the echo is just beginning. Imagine a river. It is a wide, deep river flowing smoothly towards a precipice. The water is clear and cold, moving with a gentle purpose. Now, imagine a fish swimming in this river. The fish is a strong swimmer. It can move upstream, fighting the current, or it can drift downstream, carried by the flow. Let us say that the maximum speed of the fish is 10 miles per hour. As long as the river flows slower than 10 miles per hour, the fish has freedom. It can choose its destiny. It can swim back to the source. It can communicate with the fish upstream. But as the river approaches the precipice, the waterfall, the current accelerates. It moves faster and faster. Eventually, there comes a specific line in the water, a point of no return, where the speed of the river exactly matches the speed of the fish. If the fish crosses this line, it is doomed, even if it swims upstream with all its might. Swimming at its maximum speed of 10 miles per hour, the water is dragging it backward at 11 miles per hour. To an observer on the bank, the fish is moving backward, swept inevitably over the edge. The fish is trapped. Its voice, its movement, its very existence is swallowed by the speed of the flow. In the strange and beautiful language of physics, this river is a black hole. The fish is a wave of light. And the line where the current exceeds the swimming speed is the event horizon. For decades, we believed that this phenomenon was unique to gravity. We believed that only the crushing mass of a collapsed star could create a trap so strong that nothing could escape. But in the quiet laboratories of the 21st century, physicists have discovered that you do not need a star to build a black hole. You do not need gravity at all. You can build one out of sound. You can build a sonic black hole. And in doing so, you can unlock the deepest secrets of the quantum vacuum. If you are finding a sense of wonder in these analogies, and if you enjoy seeing the patterns of the universe reflected in the flow of a river, please consider subscribing to the channel. I am Walter, the explorer, and it is my privilege to be your guide through these fluid mysteries. Currently, 73% of the curious minds traveling with us have not yet subscribed. By joining us, you help us construct these stories and ensure that we can keep exploring the boundaries of the known world together. Thank you for swimming upstream with us. Now, let us return to the laboratory and the trap of silence. The scientific name for a sonic black hole is a dumb hole. This is not an insult to the hole's intelligence. It is a pun. Dumb, in the Old English sense, means mute or silent. A black hole of light is black because light cannot escape. A black hole of sound is dumb because sound cannot escape. It is a region of silence from which no echo can ever return. To create such a thing, scientists like Jeff Steinhauer at the Technion Institute in Israel turned once again to the magical substance we explored in Chapter 3, the Bose-Einstein condensate. They took a cloud of rubidium atoms and cooled them down to a fraction of a degree above absolute zero. In this state, the atoms act as a single quantum fluid, a superfluid with zero friction. This fluid is the river. Using lasers, the scientists created a trap. They forced the fluid to flow. By manipulating the potential energy of the trap, they created a waterfall, a region where the fluid accelerated rapidly. In the calm region, the fluid flowed slowly. In the waterfall region, the fluid flowed at supersonic speeds, faster than the speed of sound in that medium. Remember, sound is a phonon. It has a speed limit. In a Bose-Einstein condensate, the speed of sound is determined by the density and the stiffness of the fluid. Let us call this speed Mach 1. As the fluid accelerates towards the waterfall, it crosses the point where the flow speed equals Mach 1. This is the acoustic event horizon. Any phonon created inside the supersonic region, any sound wave trying to travel upstream, is like the fish. It tries to move against the current, but the current is faster. The sound is swept backward, deeper into the hole. It can never reach the listener on the other side. This experiment was a triumph of fluid dynamics. It proved that the mathematics of black holes is not limited to gravity. It is a universal property of waves flowing through a moving medium. But the scientists were not just trying to trap sound. They were hunting for something much more elusive. They were hunting for a ghost predicted by Stephen Hawking in 1974. Stephen Hawking famously realized that black holes are not truly black. He applied quantum field theory to the curved space-time near an event horizon and discovered that black holes should emit a faint glow of particles. This is known as Hawking radiation. The theory goes like this. The vacuum of space is not empty. It is teeming with virtual particles. These are pairs of particles, matter and antimatter, that pop into existence, borrow energy from the vacuum, and then instantly annihilate each other, returning the energy to the void. They exist for such a short time that they are not real in the classical sense. They are fluctuations. But near an event horizon, something dramatic happens. A pair pops into existence right on the edge. One partner falls into the black hole. The other partner stays on the outside. Suddenly, they are separated. They cannot annihilate. The particle inside is lost forever. The particle outside is now stranded. It has no partner to destroy it. So, it becomes real. It steals energy from the black hole's gravitational field and flies away into the universe as radiation. For 50 years, this was just a theory. We could not see Hawking radiation in the sky because real black holes are too big and too far away. The radiation is too faint, drowned out by the cosmic background noise. But in the sonic black hole, the physics is exactly the same. The vacuum is the quiet superfluid. The virtual particles are pairs of virtual phonons, tiny vibrations appearing and disappearing. Jeff Steinhauer and his team listened to their dumb hole. They tuned their detectors to the very edge of the acoustic horizon, and they heard it. They observed pairs of phonons appearing out of the silence. One phonon fell into the supersonic flow, swept away to its doom. The other phonon, its entangled partner, escaped upstream, away from the horizon. This escaping phonon was Hawking radiation. They had created a quantum glow of sound. They had proven that the vacuum itself, when ripped apart by a horizon, bleeds particles. This discovery is profound because it connects two disparate worlds, the world of gravity and the world of quantum mechanics. It suggests that the fabric of space-time behaves very much like a fluid. If sound waves in a fluid and gravitational waves in space-time follow the same rules, does that mean space-time is made of something granular? Is gravity just the hydrodynamics of the quantum vacuum? The experiment also confirmed the role of entanglement. The phonon that escapes and the phonon that falls in are entangled. They share a quantum link. This is crucial for the famous black hole information paradox. If the black hole eventually evaporates, what happens to the information that fell inside? The entanglement observed in the sonic black hole suggests that the information is encoded in the radiation. The escaping sound carries the memory of the partner that was lost. Imagine standing next to a waterfall that is perfectly silent. You scream into it, and your voice disappears. But then, if you listen very closely to the edge, you hear a faint, ghostly whisper coming back to you. It is not an echo. It is a new sound, born from the tearing of the vacuum. It is the universe compensating for the loss of your voice. This sonic Hawking radiation is incredibly weak. In the lab, the temperature of this radiation is in the nanokelvins, billionths of a degree above absolute zero. But it is there. It is a fundamental property of horizons. This implies that sound can be created from nothing, provided you have a horizon to tear the vacuum apart. It implies that silence is just a balance of virtual sounds annihilating each other. Break the balance, and the silence sings. But there is a darker implication to this experiment. If a sonic black hole can emit radiation, it loses energy. The energy to create the phonon comes from the flow of the fluid. Slowly, over time, the radiation drains the energy of the waterfall. The flow slows down. The horizon shrinks. Eventually, the sonic black hole evaporates. This confirms Hawking's prediction that black holes die. They are not eternal. They leak their mass into the universe as radiation until there is nothing left. We are simulating the death of the most powerful objects in the cosmos using a drop of cold atoms in a university basement. We are holding the life cycle of a star in a magnetic trap. As we ponder the sonic black hole, we must ask, what happens to the sound that falls in? Inside the supersonic region, the phonon is swept downstream. But does it hit a singularity? In a real black hole, the singularity is a point of infinite density, where the laws of physics break down. In the sonic black hole, there is no singularity. The fluid just flows until it hits the end of the trap. This suggests that perhaps in the real universe, there is no singularity either. Perhaps the bottom of a black hole is just a region of exotic matter, a different phase of the space-time superfluid. Perhaps the sound that falls in does not die, but is transformed into something else. Maybe it emerges in another universe. Some theories propose white holes, the reverse of black holes. A white hole is a region that nothing can enter, but things can only leave. It is a fountain of space-time. In the lab, scientists have created white dumb holes by reversing the flow. They have seen sound waves bouncing off the horizon, unable to enter, piling up in a laser of sound. We are beginning to see that sound is a key that unlocks the geometry of the universe. It is not just a passenger, it is a structural element. The phonon is a probe that reveals the texture of reality. We have traveled a long way. We started with the simple vibration of air in a room. We went down to the atom. We saw the phonon. We saw it turn to heat. We saw it float as negative mass. We saw it connect across space in entanglement. We heard the gravitational waves of the vacuum. And now we have seen sound created from the nothingness of the event horizon. The boundaries between sound, light, matter, and gravity have dissolved. It is all vibration. It is all fields. It is all a dance of energy. But every dance must end. Every song has a final note. If the universe is a symphony of vibrations, what happens when the energy runs out? What happens when the black holes evaporate? What happens when the stars burn out and the crystals cool down? Is there a final silence waiting for us at the end of time? Or is the zero-point motion, that unkillable quantum jitter we discovered in Chapter 2, truly eternal? In the final chapter of our journey, we will travel to the end of the universe. We will ask if sound can survive the heat death. We will explore the concept of time crystals, clocks that tick forever without using energy. And we will ask the ultimate question: if the universe is a sound, who is the musician? The river flows into the dark. The fish is swept away. But the whisper remains. Have you ever watched a pendulum swing back and forth, counting the seconds as they slip away into the past? Tick, tock, tick, tock. It is a hypnotic rhythm, a heartbeat of mechanical time that seems like it could go on forever. But we know that it cannot. We know that eventually the air resistance will steal the energy from the swing. The friction in the pivot will grind the motion to a halt. The gravity that pulls it down will eventually win, leaving the weight hanging motionless, dead and still, pointing straight down at the center of the earth. This is the law of entropy. This is the second law of thermodynamics, the grim reaper of physics that tells us that disorder always increases. It tells us that energy always spreads out. It tells us that every song must end, every vibration must fade, and every clock must stop. We have been taught that the ultimate fate of the universe is a state called the heat death. In this terrifying vision of the future, all the stars will burn out, all the black holes will evaporate, all the temperature differences that drive the engines of the cosmos will equalize. The universe will become a vast, cold, dark soup of particles, drifting aimlessly in a void where nothing ever happens again. In this final state, there can be no sound, because sound requires energy. It requires a change. It requires a difference between here and there. If everything is the same, if everything is at equilibrium, then the universe is truly, finally silent. But what if I told you that this ending is wrong? What if I told you that in the deepest, coldest quantum basement of reality, there is a clock that ticks without batteries? What if I told you that there is a form of matter that repeats itself in time, just as a crystal repeats itself in space, creating a rhythm that can never be silenced, not even by the end of the universe? We are about to take the final step of our journey. We are about to meet the time crystal. And in this strange, impossible object, we will find the answer to the ultimate question. Is the song of existence eternal? If you are finding a sense of peace in these contemplations of eternity, and if you wish to be part of a community that looks into the face of the infinite without fear, please consider subscribing to the channel. I am Walter, the Explorer, and it has been the journey of a lifetime to walk these paths with you. Currently, 73% of the wonderful souls listening to these stories have not yet subscribed. By joining us, you help us keep the light of curiosity burning in the dark, and you ensure that we can continue to ask the questions that define who we are. Thank you for traveling to the end of time with me. Now, let us look at the crystal that breaks the laws of time. To understand a time crystal, we must first understand a normal crystal. Think of a diamond, or a grain of salt, or a snowflake. In these objects, the atoms are arranged in a repeating pattern in space. If you move a certain distance to the right, you see the exact same arrangement of atoms. This is called spatial translation symmetry breaking. The atoms have chosen a specific spot to sit, breaking the perfect uniformity of empty space. They have created a structure. In the year 2012, the Nobel Prize-winning physicist Frank Wilczek asked a question that sounded like science fiction. He asked, if atoms can arrange themselves in a repeating pattern in space, can they also arrange themselves in a repeating pattern in time? Could there be a system that, in its lowest energy state, its ground state, where it cannot lose any more energy, still moves? Could there be a system that flips back and forth, or ticks like a clock forever without burning any fuel? For years, other physicists said no. They said it was impossible. It sounded too much like a perpetual motion machine, a device that creates energy from nothing. And we know that perpetual motion is forbidden. You cannot get something for nothing. If a clock ticks, it must use energy. If it uses energy, it must eventually stop. But Wilczek was thinking about something subtler. He was not talking about a machine that does work. He was not talking about a clock that you could use to power a light bulb. He was talking about a system that breaks time translation symmetry. In a normal ground state, matter is static. It looks the same at 1 second as it does at 2 seconds. It is constant in time. But in a time crystal, the ground state itself is a cycle. The matter changes configuration, tick tick-tock, tick-tock, and returns to its original state over and over again. And crucially, it does this without losing energy, because it is already at the bottom of the energy well. It cannot go any lower. The motion is not spending energy. The motion is the state of existence. It took 5 years of intense debate and experimentation, but in 2017, 2 separate teams of researchers, one at the University of Maryland and one at Harvard, proved that time crystals are real. They created them using chains of ions and impurities in diamonds. They hit these systems with a laser pulse to set the rhythm. But here was the magic. The system did not respond at the frequency of the laser. It responded at its own frequency. It created its own time. If the laser pulsed twice, the crystal might pulse once. It broke the symmetry of the time flow. It locked into a rigid, repeating heartbeat that was robust against noise and perturbation. This discovery changed our understanding of the fundamental nature of matter. It proved that rhythm is not just something that happens to matter when you add energy. Rhythm is a possible state of matter itself. Think about what this means for the end of the universe, when the last star dies and the last black hole evaporates, and the universe cools down to absolute zero. We used to think that all motion would cease. We used to think that the phonon, the particle of sound, would vanish. We thought the universe would become a static, frozen graveyard. But if time crystals can exist, then the freezing of the universe might not be a stillness. It might be a locking. The matter of the cosmos might settle into a state of eternal vibration, a heartbeat that continues forever in the dark. This is a form of zero-point sound. It is a sound that requires no listener, no air, and no energy source. It is the sound of existence affirming itself. It is the universe saying, "I am," over and over again, in a loop that defies the concept of an ending. This brings us back to the very beginning of our journey. We asked, what is sound made of? We started with the air in your room. We saw that sound is made of collisions. It is made of chaos. It is the transfer of energy from one molecule to another. Then we looked deeper into the solid crystal. We saw that sound is made of phonons. It is made of quantized steps of energy. It is a particle. Then we looked at the superfluid. We saw that sound is made of flow. It is a frictionless ghost that can split into heat and vortices. Then we looked at the black hole. We saw that sound is made of pressure waves in the hot gas of the galaxy, a mechanism that regulates the birth of stars. Then we looked at the vacuum. We saw that sound is made of gravity. It is the stretching and squeezing of space-time geometry. And now, finally, we look at the time crystal, and we see that sound is made of time. It is the breaking of the symmetry of the moment. It is the fundamental tick of reality. So, who is the musician? If the universe is a symphony of entangled drums, ringing vacuums, and eternal crystals, who wrote the score? The answer, suggested by quantum mechanics, is that there is no separation between the musician and the instrument. The universe is a self-exciting circuit. It is a system that observes itself, and in observing, creates the reality it perceives. You are not separate from this. You are not a stranger sitting in the audience watching the show. You are made of the same vibrating fields. The atoms in your ears, the neurons in your brain, the electrons in your blood. They are all singing the same song as the stars and the time crystals. You are a localized concentration of the cosmic melody. You are a knot in the web of entanglement. When you speak, you are creating phonons that will eventually turn into heat, warming the universe by a fraction of a degree. That heat will scramble, but the information, the quantum truth of your voice, is never truly lost. It is woven into the thermal background of the cosmos, and when you listen, you are collapsing the wave function of the world. You are deciding which version of the universe becomes real. You are the conductor of the moment. The silence that you feared, the silence of the empty room, the silence of the deep space, the silence of the grave, is an illusion. There is no silence. There is only the limit of your hearing. Beyond your ears, the air is crashing. Beyond the air, the vacuum is rippling. Beyond the vacuum, the quantum fields are fluctuating. And at the end of time, the time crystals are ticking. The universe is a song that cannot stop singing. It is a bell that was struck once at the Big Bang, and the ringing is what we call reality. As we close this book of sleepy science, I want you to try one final experiment. Tonight, when you lie in bed in the quietest moment of the night, try to listen. Do not listen for the traffic. Do not listen for the wind. Do not even listen for your heart. Listen to the hum of your own presence. Listen to the fact that you are here, a conscious being in a universe that allows consciousness to exist. That feeling, that awareness, is the highest resonance of all. You are the echo of the Big Bang. You are the ripple in the superfluid. You are the witness to the time crystal. The universe is vast, and it is old, and it is strange, but it is not silent. And as long as you are here to wonder about it, it never will be. Sleep well, explorers. The journey is infinite, but for now, the story rests.